Hello, welcome to the lecture for Monday, September 10th. I've got our schedule up, so I will start there as normal. So today I'm going to finish up the rest of Chapter 2. Last time we had finished off I had covered test of independence, so we had talked about the chi-square test and the likelihood ratio test, and I had started covering R coding for that. So I have a little bit more to finish up on R coding, so I'll start there. And then we'll talk about test of ordinality and exact inference. So that will be today's lecture. And then Wednesday we'll pick up and we'll move into Chapter 3 and start talking about generalized linear models. So that'll move us into the modeling section of the course. And in terms of homework assignments, I've got a number of your homework 2s, and assuming I have all of those on Wednesday when I come in from my trip, I will start grading those. And then homework 3 is due this week. So if you have any questions, definitely bring those to office hours or class on Wednesday. All right, with that, let's pull out our R coding where we had left off. So I had just talked about getting out, let's see, so I've got my chi-square. So I'd gone through, I'd done my chi-square test. I had showed you how to get the expected values out, the observed values out, and I'm going to go ahead and execute all of this. So make sure we have everything in memory. I don't need that help. Great. So I'm going to do my chi-square test, and I had just talked about how you can pull out your expected values. So with the $ expected, so that's what I've just done. So these are our mu ij's. And then you can also get back your observed. So those are just your counts by using the $ observed. And those are useful if you want to compute your statistics, quote, by hand. And then I go through and I talk about what is called residuals in there. And I just want to remind you that those are not the actual residuals that you want to use. The thing that they call residuals in there is actually the observed minus expected divided by the square root of the expected. So that's not what you need to use for your residuals. What you need to do, and I had showed you the formula, so I'll pull up our slides in a second. But if you want to get to the coding of that, that was what was next in the R script. And so the first thing I was doing, so this first line I've got highlighted here, I'm summing up all of my counts. So that's just an easy way to get my sample size. So PD is just the table. So if I sum all of the counts in my table up, and I saved it as N, so that's my sample size. And the reason I wanted to do that is I'm going to show you just a piece of this code. Okay, so I'm highlighting this margin table part. So if I execute that, and let's see, so when I execute run liner selection, what that's giving me is my marginal for my row. So it summed over for the white voters, it summed over for the black voters. And then at the end, you see I've got this divided by N. So if I execute this whole thing, it's giving me the proportion of white and the proportion of black voters. Right? So take the marginal table for the row, divide by your sample size. That's going to give you your pi hat I plus. And then I do the same thing, but I repeated it here, but for the columns. So if you want to execute each piece of the command, so if I just do the margin table and I run that, then that gives me the sum down for each of the columns. So the number of Democrat voters, independent voters, and Republican voters. And then at the end of that, you'll see I have it divided by N. So that gives me my pi hat plus I's. So those are my estimated proportions for the types of party affiliations. And in my code, I actually saved those. So p.race and p.party, just to help me remember that those are my estimated proportions for the race and for the party variables. And then I need my standard error. Okay, so standard error is the square root, and then I need my expected value times, and then I have 1 minus p and 1 minus my other p. So let me pull up my slide right? So if you look at the bottom, this is my standard error in the bottom. So I need my expected values. Those are my mu hats. And then I need my 1 minus pi plus and my 1 minus p plus j. Right? So I can compute all of that. And if I piece this apart, right, so chi-square expected, so that piece right there, again, gives me just my expected values. And what I want to do, so when I execute this first piece, I'm going to take, so let's see what that does. Oops, no, actually, I need to do this last piece first. Right, so let's look at what this does. So first of all, 1 minus the probability of race, right, gives you 1 minus for the white and the black. And if I do this for the party, that gives me 1 minus for that as well. This symbol right here is going to do a piecewise multiplication. So you're going to end up getting the Kronecker product for those who know the math term for that. But let's multiply it and look at what it looks like. Right? So what it's done is it's taken the probability 1 minus p race, and for each of those, so 1 minus white, 1 minus black, it's multiplied that for Democrat and it's put it down here. It's multiplied that for independent, it's put it down here. It's multiplied that by Republican and it's put it right there. So you've got the cross tabulation of 1 minus white, 1 minus Democrat, and that's in then the cross right there. And then I took the square root. So this whole thing that I've just highlighted here actually gives me all of my standard errors that I need, right? So what's nice about this is this one command calculated all of the standard errors for all of the cells. And then if I go, so if I look back at what that statistics form looks like, right, I've got my observed minus expected divided by my standard errors. And that's exactly what this command is doing. So observed minus expected divided by your standard error. So those are the correct residuals, right? So that is actually what is saved in your STD-RES, right? So you don't have to calculate it. What I wanted to do was show you that that's the correct residual, and that's one way that you could calculate it if you wanted to do it by hand. It's also a good way to just validate the first time you pull something out of an R function that you know exactly what it's computing for you, right? So this is a validation that, yes, the STD-RES are computing the standard error the way that we expect it to for a binomial count, and correctly counting the residuals by calculating the residuals by using that standard error. Right, so these are all of our residuals, and we had discussed that if you have a large enough sample, that you could assume that those are a standard normal. And this last line calculated then p-values for you. Inherently, if you get something all the way out in the tails past 8, we know that's going to be really unlikely. Something that's close to 0, we know is pretty likely under the null of no association. And so that's why you've got p-values close to 0 for Democrats and Republicans and close to 1 actually for independents. I also show you in here how to compute your chi-square test. And if you look, so I saved my expected, I saved my observed, and that goes there. So I just submitted that. And if you look inside, you'll see I've got the formula piece for my likelihood ratio. So if we back up to where that was computed, observed log, and then I've got my observed divided by expected. So let's look in here. Observed times the log, this is the natural log, and then in parentheses I've got observed divided by expected. So if I just highlight and execute that one piece, you'll notice it gives me those values for everything. So for all of my 6 cells, and what I actually need to do is sum them up. Okay, so that's what's on the outside. So it's going to sum up everything in here. And then my statistic had a 2 on the outside. So here, that computes, that whole thing does my entire likelihood ratio statistic for me. So I've got a value of around 90.33, and I actually just copied and pasted that into here. Degrees of freedom. So we had talked about that it had 2 degrees of freedom because it's a 3 by 2 table. So I've got to compute my p-value. I can do p chi-square. I need the probability of something larger than that. So p chi-square gives me the probability smaller. So that's why I need a 1 minus. So my p-value again is really small. And if you wanted to, you could use this function here. So compute g squared. What it takes is your data table. So if you were to execute this piece, so you could put this into, say, the top of a script that you're running, and this will save the function that you can use. So compute.g squared now will act as a function like any of the other functions that you've been using that R has created. And in particular, right here, so compute.g squared, and then I give it my contingency table. It automatically did everything in here for me, right? So all you'd have to do, change nothing, but copy this function and paste it in and put it into your R code. And then the only thing you'd have to change is that you would feed it the correct contingency table, and that'll compute your g squared statistic and return your p-value for you. And since I wrote that, if you get any errors, let me know so I can do some error checking, but I think that'll work just fine. All right, so that gets you up to where we had left off. So we did I went through here, talked about my likelihood ratio test. Here are our residuals. So these are our adjusted residuals, and that they adjust for our standard error. And then these are, I just pulled the residuals off of my code, put them in the table to look at them for you. And noting, once I've computed my p-values, that these give us p-values of approximately 0 for the first and the latter column, and then 0.82. So then the question is, given that we know that there is a large departure from independence, what would you conclude? And so I think we had started kind of talking through this as we went through the lecture and through the analyses, but things that you might want to jot down. So clearly there is a departure from independence. And this is for a person's race and their political party affiliation. And you might want to put one of the statistics. So g squared was, 90.33 with a p-value of essentially 0. And you could also put your chi-square test in there as well. And then you could say in particular, let's see. So we saw, the number of white Democrats. So one thing that we had noted, so the number of white Democrats is lower than expected. I get that because this is a negative. And the number of black Republicans is also lower than we'd expected by chance. In particular, so the number of white Democrats and black Republicans is much lower than would be expected if there was independence. And then you might want to add on, since it does look like there appears to be no association between race and the independent affiliation, you could say that within the independent party affiliation, you could probably say it better than that, would be my guess. All right, so that's what you could get out of that. So residuals at least take you that next step further. So if you think back to when you've done an analysis of variance, so a lot of times you'll do an analysis of variance, you'll find that there is a departure, and then you want to know, okay, well, what? So there are differences. Where do they exist? Adjusted residuals for your chi-square tables take that next step. So what actually is differing? So another way to look at where differences exist is to partition your chi-square statistic. And I'm going to mention one way of doing this. And this corresponds specifically to the likelihood ratio statistic, because here we're going to be able to take your likelihood ratio statistic and decompose it into a smaller set of independent chi-square statistics. So one way to do this is to start by taking your first two columns of a 2x, so this will be a 2x2 table if you're taking your first two columns, and compute a likelihood ratio test for that. The next thing you would do is then construct another 2x2 table, but you're going to combine the columns 1 and 2 and compare them then to the third column. And then you keep going until you get to the last column, and the last column is then going to be compared to the summed columns of 1 through j minus 1. Right, so this probably is a little better to understand when you do it by an example. So for us, we have our political example. So if I'm going to take just our first two columns, that was the Democrats and the Independents. Okay, and then I have the same rows, so white voters versus black voters. And so the first step is just to take your first two columns. So the first counts for those two columns are 341, 103, 105, and 15. Oops, 15. So that's literally pulled directly from your table. So if you see back, all I did was pull these two out. So your next step is going to be to construct another 2x2 table. One of our columns is going to be the next column, so this will be the Republican column, and it's going to be compared for a departure from the sum of the columns before it. So we'll sum up, so 341 and 105, and that will go in to the column that we need to compare for Republicans, and then 103 plus 115. So let's go back down to make that table. So this then will be Democrats and Independents versus Republicans. We still have white voters, and we have black voters. So if you sum those up, you get 446 and 118. So 341 plus 105 is 446. 103 plus 115 is 118. So that's where I've got this first column. And then I'm just going to pull the last column out. So 405 and 11. And what you can do then is take these two tables and compute a likelihood ratio test. And if you do that, so that'd be a good practice for you to practice your likelihood ratio statistics. The first table has a likelihood ratio value of 7.156 and 83.175. And with this type of partitioning, you actually get, so they're independent chi-square tests, and they completely explain the full likelihood ratio test. So these come out to be, let's verify that. So they come out to actually be the same likelihood ratio value. So this would actually be a good practice for that function that I said. So you could take the function that I created for computing likelihood ratio test, feed these two tables in there, and look at what you get back. So from here, if you are comparing each of these, so since they're 2x2 tables, okay, what would they be compared to in terms of a distribution? Right, so they'd be compared to a chi-square 1 distribution. So you still see that there is an association. So our chi-square 1, so a traditional critical value for that test would be at an O5 level, you have a critical value of 3.84, right? So both of these are well past that. So for each table, you'd still conclude that there is dependence between a person's race and their political affiliation. But you see that there's a much larger deviation that comes from the distinction between Democrats and Republicans. So you might want to just point out something like, and we got that again from the overall table. So while there is association between Democrats and independents with respect to party affiliation, the largest difference exists between Democrats and independents and Republicans. Oops. Right. So I might argue that you really got more out of the conclusions here when you looked at the cells individually, since we were able to see specifically the large deviations in Democrats, large deviations in Republicans, and the independents didn't contribute to the deviation from independents. Whereas here, the independents are kind of getting a little bit murky since you've got them combined into two different tests. But this may make more sense in different scenarios where there's a natural combination between the classes. So that might be something to keep in mind. All right, so you have that script up. I do encourage you to go through, play with it, execute pieces of the commands. That's probably the best way to learn each of the commands that you don't know, and just change some things and see what happens. All right, so that is a test of independence. So G squared, chi-squared. Then we talked about ways to see where the differences are happening. If you notice the orders of the rows, the orders of the columns, when we're testing for independence, they didn't make any difference, right? So what order a row or a column was put in made no difference, right? So this is getting to the point that tests of independence are just working off of having nominal variables. So if we have an ordinal variable, we may want to use that information, right? And in particular, if there is an actual relationship between a variable's ordinality and something, we're going to have more power to detect an association if we use that. So here I'm giving you an example data set, and this is a small study. So I pulled this from, let's see, Western Australian study of hypertension, alcohol, and obesity. And I've got the contingency counts actually summarized in the table. So I've got 3 different levels of obesity, 2 levels of hypertension, so high, low, and then different classes of how many drinks per day a person has, and then how many people correspond to that combination. So 5 people had a low level of obesity, had hypertension, and didn't drink any alcohol per day. Right, so we could take and look at pairwise associations here, go through, do a test of association between, say, the number of drinks per day and obesity, or a test between the number of drinks and hypertension, and see what happens. So is there dependence between those different pairs of variables? But all of the variables are ordinal. Right, so we might want to think about how could we use that information to gain power to detect an association between them. Okay, so that's what we're going to do next. So we've got 3 ordinal variables. So one's low, medium, high, absence, presence is the other, and number of drinks per day being the last one. And really what we're doing is we're looking for a trend between variables. And so you can connect this back to correlation, only we've got only a few number of values that a variable can take. So what we're going to do is think about assigning scores to the levels for our 2 variables. And so we might say we've got U1, let's see, less than or equal. There's my less than or equal. So we're going to assign monotone scores. So U1, U2, all the way up to, and we have UI. And we'll do the same thing for Y. So we've got Y, and we'll assign something, right? So these will have to obviously make sense, and that's going to be something that we'll need to think about. So what will make sense when we go through and assign scores? Sometimes there'll be natural scores to actually assign, and sometimes there won't, right? But we'll always want to assign monotone scores. So we've got U1 less than or equal to U2, all the way up to UI, and likewise with our scores for Y. So we have our scores, and we actually, if you assigned your scores, one way to think about whether there's a trend between X and Y is to take those scores and go through and calculate a correlation, right? So this messy formula here is just taking the scores, recognizing that you've got a fixed number of counts for each combination of your levels of your variables and calculating correlation. So you could just throw all these scores in, calculate Pearson correlation if you've represented them as individual observations. One common statistic that is used is the M-squared statistic. So this is going to test the null hypothesis of no correlation versus the alternative hypothesis of having correlation. So we've got, and it's much easier to write, but we'll do what we can. So the null is that we have no correlation, and this is versus an alternative, and we have non-zero correlation. Although there may be times when you're actually interested in testing for a direction, right? So rho not equal to 0. Although actually this one is not set up to be able to do that. So you might have to look at how you would construct that. I'll take the square root. That should actually work. All right, so we're interested in testing that. So for large samples, we can go through, calculate your correlation, and you can use a chi-square random variable with 1 degree of freedom. And notice the difference between these. So if we were going to ignore the ordinality and go through and do a likelihood ratio or a chi-square test, then we would be using I minus 1 times j minus 1 degrees of freedom for a chi-square distribution. If you have ordinal variables, you're using only 1 degree of freedom, right? So you end up with a much less drastic comparison for your null, right? Because you have a chi-square then with a mean of 1, right? So your statistic is not going to have to be nearly as extreme before you can detect a deviation from your null. All right, so we've got our m-squared. So let's take a look at our example. Right, so again, you have to think about what your scores would be. And so for us, we had obesity, which was low, medium, and high. And we had hypertension, so it's high blood pressure of no and yes. And then we had drinks, which was 0, 1 to 2, 3 to 5, and then it was 6 and greater, 6 and on. So scores. So at this point, essentially you have to think out about what would be logical. Low, medium, and high. So if you felt that they really were representing the spectrum of low, medium, and high, as opposed to something that was less centered, then you could give these scores of 1, 2, and 3. So this is going to be where you're going to have some kind of a content expert help you figure out what scores would really make sense. Hypertension, yes and no. That seems an obvious in terms of no is going to be 0 versus a 1. Since it actually only has 2 levels, this is not going to matter. But we'll go with 0 and 1. And then drinks. So drinks, since it actually has a numerical piece of information in there, it's a little easier to get to. So drinks of 0. For the 1 to 2 class, often you might want to use just the average value of the class representation. 3 to 5, so I could use a 4 drink representation. The endpoints are hard, so 6 and over. So what would be a typical value? I just pulled 7, right? So 7 I thought would represent the fact that there are going to be some observations over 6. We'll have to come back and think about, well, what if we were wrong? What if that's not a good representation for your score? Another option, so another thing that you'll see done is something called the midrank. Right? And with the midrank, the idea is you want to, so within each category, you're going to rank the observations, right? So literally you're going to go through within the category, you're going to rank them, line them up in the order of their ordinality, and then you're going to label them off 1, 2, 3, 4, all the way to n, right? So you're going to rank the observations, and then for each category, use the score that is the mid rank of that category. Right, so again, we'll look at what that would actually be for our particular example. So let's look at the obesity category. So for our obesity category, let's look up at our, let's see, obesity. So I've got all of these that were low. And I'm going to go through and show you some tabulations when we get into our OR coding. But if you add up all of these counts, you end up with 165 people that have low obesity. If you look at average, so mid-level, there are, let's see, so I ranked them actually. So 166 to 326 were medium, and 327 to 491 were high. All right, so I'm going to write that down for us. So for the obesity category, if I line them all up, 1 through 165 are low. And then 166 to 326 were counted in medium. And then I had 327 to 491. So that's my sample size is 491. Those were the high category. And so what this would tell me to do, so a mid-rank would actually be, so to take 1 plus 165 divided by 2, and that would be the assigned score for that group. And that comes out to be 83, so 166 divided by 2. And then that would be versus the next category, which would be 166 plus 326 divided by 2. Which, if you calculate that out, will be 246. And then for the last category, you would use a score that would be 327 plus 491 divided by 2, and that's a 409. So these would actually be the score that you would use for that category. And this gets closer to something that is called a spear correlation. It's a correlation between ranks, so it's related to that. And the idea is to get you something that represents the volume, the number of observations that are falling into the categories in terms of how important they are. If there truly is no association between the two different categories, then the ranks are going to just assort independently, so you will end up with no association. All right, so from here, let's take a look at some of our code. And I gave you a separate handout, actually, so you might want to turn to that. I don't think I opened that yet. So that starts off so we've got, right. So for some of you, you may not have actually read data in. And if that's the case, that would definitely be something to come in for office hours for. Especially with thinking about some of your projects, you're probably going to want to read data in. My R tutorial that I had posted, the beginning tutorial, also talks you through reading in different data sets, set types. And that's what I'm starting off with here. So let me pull in. So the very first thing I'm reading in my data, so that's my read table statement. I print out my names, I looked at the dimensions, and I printed the first 5 rows. So I always do this when I read data in. I know what my names should have been. I knew they were at the first row, and so it does print them out. And I looked at to make sure when it printed my observations that they're all formatted like I expect them to be. So this just helps me check that my data was read in correctly. Summing up my counts. So if I sum up that last column, right, so $count gets me to this variable here, and I have 491 observations. Let's see. Here, I'm doing some work to actually get, instead of having counts, I am extending this to where I have an observation for each individual. And that might be something you want to step through. So this is, I'm going through and repeating 1. I'm repeating it corresponding to how many actual counts there were for the first row. I'm repeating 2, the number of counts that corresponded to the second row, and so on. And what that allows me to do is to actually expand. And so I expanded my data set to where I had individual observations. So you'll see that what I read in was a tabulated value, and what I ended up with when I expanded it was I've got the first 5 values, which correspond to having the same levels of obesity and blood pressure value and drinks, but I've spread them out 5 times. So, all right, so that's what I did first. So tabulations. So if I want to go through and do my 2x2 tabulations, if you want to piece this apart. So inside I did a table for obesity by blood pressure. And then I also, on the outside, I added margins to it, right? So this is getting me my 3 different 2x2 tables. So you can play around with those if you want to look at how many counts you have. What else did I do? So here I checked the number of rows in my individual data set, 491, so that's correct. And then I saved it, so that's my sample size count. Since I have my scores already loaded, let's see. And, oh, that is right. I should mention. So when I posted your data sets, so let's open that up. I didn't post them in low, medium, and high. I actually posted them with the scores already listed. And this is a good point to make. So I had the original data set labeled as low, medium, and high, and the different intervals for the drinks. There's a way to code this and recode it within R, being a little fancier. Oftentimes it's quicker just to do search and replace in Excel or a text document. So that's actually what I did. So this data set that I read into R already has my scores substituted in, right? So here's my 1, 2, and 3, my 0 and 1, and then the scores I decided on for my drinks, right? So there's nothing wrong with doing that. So I have my scores. I am then going to calculate the correlation, right? So this is why it was important for me to put individual observations in. That way it can appropriately weight for the number that were observed within my data set, right? So this would be my correlation between my ranks. And then my m squared, so my formula is n minus 1, and then the square of the correlation. So there's my square. So I'm going to save it and print it. Right, so I end up with an m squared of 11.27, and that is for comparing obesity with blood pressure. And then since that is, I want a p-value, right? So already we know it's going to be pretty much 0, but if you want to get double check, probability of being greater. So I have my 1 minus, and here's my chi-squared. Here is the value, so m squared, and then degrees of freedom is 1. So that would give you your actual p-value. And then I went through and did the same thing comparing obesity to drinks. And so executing that, that is less extreme. So you end up with a chi-square m squared value of 5.23, a p-value of 0.02-ish. And then I did obesity to drinks. So that's the one I just did. Blood pressure to drinks is the last of the 3. So comparing that, you again get a pretty strong relationship between the two. So m squared is 8.15 and a p-value of 0.0043. So you're still seeing pretty significant trends. And in fact, if you look at your notes, let's go over here. And I have a table for that. So let's start putting in some of these values. So for your m squared, let's see, so blood pressure versus obesity, look back, 0.00079 is what I had. Let's double check though, 0043 and 0.022. So blood pressure versus obesity, blood pressure, let's see, what do we have here? So blood pressure versus obesity, yep, there's my 0.0079. And then obesity versus drinks, yes, so that was my 0.022. And then I have blood pressure versus drinks, which is my 0.0043, right? So those are my m square statistics, p-values. So you might want to see how would this compare if I did my chi-square and my g-square. Right, so the chi-square.test will do that for you. You have to tabulate your data, right? So I've got my table statement in here. I am going to use my compute g-squared function. So this will give me my chi-square test. This will give me my g-squared test. And let's do obesity versus hypertension first. Right, so my chi-square gives me a p-value of 0.0029, and my likelihood ratio gives me a p-value of 0.0030. So why don't you go ahead and fill in the rest of that table. So this is blood pressure, so this was an 0.0029, and this was an 0.0030. Right, 0.029, 0.030. Okay. Then I'm doing the table for obesity versus drinks. Actually, let's do the second row. So the second row of that table we're working on is blood pressure versus drinks. So that is this. And you get so the chi-square test 0.026 or 0.0259. And for your g-squared 0.0221. All right. So here we've got 0.0259 and 0.0221. And then our last set, so the last row had obesity versus, did I mix those up? Oh yeah, obesity versus drinks, that's correct. So I execute that, and that is 0.3253 versus 0.3166, right? And 3166. All right, so that's going to be something interesting to come back to. But let's do the mid-ranks as well. And again, so rather than bothering with doing fancy coding in R, Not that I couldn't do that, but sometimes it takes less time to just recode and add a column in Excel, and so that's what I did here. So this data set I created in Excel, and I added in Excel these 3 extra columns, which give the obesity rank, the blood pressure rank, and the drink rank. And so I'm going to read that into R and use those ranks. So let's see. And then I have to do the same thing. So when I read this in, you'll see it read in obesity rank, blood pressure rank, drink rank. I need to expand it out so that instead of having counts, I actually have data per person, which is exactly the same thing I did earlier. And then I'm going to go through, calculate the correlation, calculate your M squared. So this is for comparing the obesity to the blood pressure rank, right? And I end up with a very comparable value. So 0.0079, right? What else? Let's see. Then I've got obesity compared to drinks, right? So that is a tad bit different, but not much. And then when I compare blood pressure to drinks, that is a little bit different, but not terribly different. So let's transfer those over and then take a look at all of our results. So for, let's see, M squared based on mid-ranks, so 0.0079 for blood pressure versus obesity, that was the first one. Obesity versus drinks, which is actually the last row, is 0.0226. And then we've got blood pressure versus drinks, which is actually the middle row, is 0.0033. All right. And so from looking at this, so for blood pressure versus obesity, blood pressure versus drinks, you've got a little bit of wiggle room, but not too much. And one thing to remember is that, so blood pressure was dichotomous. So you're not going to get a huge amount of change because it doesn't matter what you coded blood pressure as. It could be 0.1, it could be 0.2. Yeah, you have a line between 2 points. So, but obesity versus drinks, obesity had 3 levels and drinks had, 4 levels? There were multiple levels, 1, 2, 3, 4 levels. And so depending on the trend that exists and what the scores are, you can get some pretty different numbers there. And one thing that you do see is that if you had not recognized that those were ordinal variables and you had just done a G-squared or a Chi-squared test, you would have completely missed the relationship between them. And so you can see that because your p-values are around 0.3. If you had done an M-squared based on the ranks we came up with, or you had used your mid-ranks, you would have detected a trend between the two. So your p-values are around a 0.02, right? So it's always important to rethink and look at, do I have any variables that might be ordinal in nature? And if they are, it's worth then going through and testing based on that ordinal information. All right, so a couple of notes on this analysis. So first of all, the scores that I used, the mid-ranks that I changed to, didn't change the p-value. And this brings up something that you always want to think about at the end is, did you use scores that make sense? Would your conclusions change if you use different scores? And it's useful to actually run a couple of different options. And this is actually called a sensitivity analysis. So I back on page 80 just to make a few notes. So it's best to attempt use of scores that make sense. Okay, that's a does statement, obviously. If you are in doubt, so if in doubt, do what is called a sensitivity analysis. Do a sensitivity analysis with a few options to see if your conclusions would change. Conclusions would change. And another thing to think about is to consider how small cell counts might affect Right, so if you're using mid-ranks and you go through and you have small cell counts, then essentially what you're going to end up doing is counting those two groups as being very similar because their mid-ranks are going to be comparable. So this is a comment that's specific to your mid-rank values. Right, versus if you have categories where you've got a ton of counts, then that particular category is going to be scored very differently from your other categories. That may make sense, it may not make sense, but that's something to consider when you're looking at how your scores are assigned. And like I said, if you are in doubt, go and do a few analyses with different options. If your results don't change, and here they did not when we used mid-ranks versus the scores that seemed logical for our variables, then you should be pretty safe. And it's always worth mentioning a sensitivity analysis was performed on this, that, and the other, and the conclusions all remain the same. A few ending comments. So comparing test of independence, your chi-squared, your likelihood ratio test, so only using the nominal piece versus your m-squared using your ordinal information. So if there actually is a trend, so if there is a trend, let's be more specific. So if there's a linear trend, then it turns out that your statistics are actually going to be pretty comparable in size. So m-squared, g-squared, and your chi-squared are all going to be pretty much comparable in size. Right, so let's think about what that would mean. So if they are comparable in size, then think about what the significance is being judged with respect to, right? So since your degrees of freedom for the m-squared are only 1, whereas for your chi-square and g-squared, they are what? They are I minus 1 times j minus 1. Right? So if your table is large, that could be considerably larger. Then the m-squared will end up with a smaller and could be much smaller p-value. Right? And if you're not quite sure about why that is, you need to think about the fact that the expected value of a chi-square is equal to the degrees of freedom, right? So the mean is equal to the degrees of freedom. And it might be worth drawing out a couple of pictures, though that would be hard for me to do here. If you have a question on that, ping me before class on Wednesday and I'll draw up a couple of pictures. But the point is, if all of these statistics are about the same size, and to be deemed large and significant, you have to be, around 4 for a chi-square 1, whereas you have to be, much larger for a chi-square 4 or chi-square 8 or chi-square 10, then you're going to end up with much smaller p-values for your m-squared test. So that said, that is if there is a linear trend, right? Okay, so the upside for the g-squared and your chi-squared is that they do give the most general alternative. Right, so in other words, they detect many patterns. Under their alternative. Okay, so that's a benefit, but they're not powerful for a specific alternative. Right, so that's going to be the case for a lot of statistics that are geared towards capturing and being robust over lots of different patterns or lots of different alternatives. Right, so that's a great thing to have because you could catch a lot of things, but if you really expect or are looking for a specific type of pattern, then you might be better off looking at the kind of statistic that's powered to find those. And so M squared, so it is geared towards and it is specific to a trend, right? So the benefit of that is it's powerful for that specific scenario. Right? And linear trends are common. Right? So it's not that this is a rare scenario that we happen to have a powerful test for. It's a pretty common scenario. But it will miss other departures. From independence. All right, so you kind of have to just recognize and think about what you're looking for. And if it all comes down to it, you might want to look at some plots. So if you'll notice at the end, I actually do a few plots. Great, so that par statement was just setting up a, making sure I only had one plot window. So what I did was to just do a box plot. And I did a box plot of, so I've got obesity, so the 3 obesity categories, and then I was looking at a box plot for drinks. So I was curious what the pattern of drinks would be over the 3 categories. And you see, it's not the best plot. I tried a couple of other plots. The other thing I looked at, so at least you could see that it does go up from 1 to 2 and 3. Right, so perhaps for the low category of obesity, you have less drinking versus having higher levels of obesity, you start getting into higher levels of drinking. So maybe that's where some of that extra information is coming from. When I did the table, so the table for drinks versus obesity, yeah, I'm not sure that I would pull that trend actually out of the table, which kind of gets to why it would be important to do more than just the tabulation, but actually start getting at what those scores are telling you. So worth looking at plots, tables, look at your statistics, think about what kind of information you've got over them. All right, I think given that we are going on almost an hour, I should stop there. And yet again, I guess I am not done with that chapter 2, darn it. And we'll start on Wednesday, so exact inference for small samples. Which means we may have to push the homework a little bit because you do have some homework on an exact problem. So if you get to that piece, if you want to just wait, we could always push that to the next homework assignment. Or if you've done some reading and want to hop into it, feel free to. Otherwise, I will start on Wednesday on slide 83, and we will get into exact inference for small samples. If you have questions, send them to me. I will try to get to them when I can during breaks of the symposium. Otherwise, I am back Wednesday morning, and I will get back with you as soon as I can. Good luck with the homework, and I will see you soon. Bye.